limit is four pages. So appendices are unconstrained, but it's, I think, considered bad taste to have like a 20-page appendix.
Oh, it is. Okay, well.
But
you have to, yeah, you have to explain anyway.
Can we start? Shall we start?
Sorry?
Shall we start now?
Yeah, of course. Sorry.
Okay. Good morning, good afternoon, everybody, and welcome to the fifth and last session of Train Data. Our first speaker today is Miranda Cheng, who will tell us about machine learning for computing in quantum field theory. Please go ahead.
Yeah. Okay, so good afternoon, evening, morning, everybody. And I would like to start by thanking the organizers for the invitation and for giving me a chance to speak here. And yeah, right. So the title is Machine Learning for Computing in Quantum Field Theory. Okay. So yeah, we have seen a lot of interactions between theoretical and machine learning, and in all kinds of different ways. And from the direction from machine learning to theoretical physics, I mean, most straightforward interaction would be to use machine learning as a computational aid in doing computations in theoretical physics. And of course, there are more conceptually deeper possibilities that are being pursued and explored. For instance, can machine just learn new physics, new laws of physics, etc.? And yeah, that's all very interesting. And in the other direction, I mean, one can hope to use insights from theoretical physics to give something to machine learning, for instance, in the problem of interpretability, and maybe to inspire different architecture designs. And we have also heard about talks in this direction in this conference. And this is also something I'm personally have been working on. But today's talk, I'm just going to focus on the most straightforward interaction, namely to use machine learning to compute things in theoretical physics. And not only is sort of the interaction sort of, straightforward and rudimentary, if you want to, but also actually the content. But first, I would like to say that this is based on a paper scaling up machine learning for quantum field theory with equivariant continuous flows. And this has been presented in the NeurIPS workshop earlier this week. And this work would not have been possible without my wonderful collaborators, Pin Han, Corrado Renon, and Roberto Bonison, and all of them affiliated with Qualcomm AI research. Right, so it's a conference on string data, so we heard also many talks on how to, use ML to do computation in the framework of string phenomenology. But my talk today is even a bit more rudimentary than that in the following sense. I mean, we would like to probe this new physics. I mean, physicists would like to disentangle new physics, no matter whether it's new particles or dark matter, etc., from data, including data gathered from the detectors or from the sky. But the zero step for doing this is that we need very high precision predictions from non-physics, such as standard model. And we cannot necessarily do that right now in a reliable fashion. And I think one of the recent example is the muon magnetic moment. You could say, there's on this graph, there has been discrepancy between theoretical predictions. So between just what SM actually predicts, and that leads to a dispute between like whether there's really new physics there or not, and something like that. So this is a perfect example of the phenomenon I just described. So yeah, what is going on? Why? Okay, so the question we would like to ask is like, can machine learning help? Right. So to answer this question, let's take a look at the computation involved. So lattice field theory has been the main computational tool for computing in non-perturbative quantum field theory, such as QCDs. Okay, of course, we know other possible frameworks, such including holography, but lattice field theory is for many people still the go-to method. So the idea of lattice field theory, well, it's kind of redundant to say this right now, but just to set the stage, just repeat it. I mean, we will replace the infamous like infinite dimensional computation with a finite dimensional one by discretizing space-time, okay, to replace it with a lattice. So in this talk, I'll be, in the Lorentzian world. In this framework, right, if you want to compute the expectation value of some operator, what do? You do a sampling. So you sample according to the physical distribution that's given by your Lagrangian, and that's usually done by Markov chain Monte Carlo or MCMC, and then using this sample, you just take an average. So that's all nice, but it's still very challenging because although we have replaced the infinite dimensional computation with a finite dimensional one, the dimension is still huge if the lattice size is large. So that caused the problem of the so-called critical slowing down, which is a term that refers to the catastrophic inefficiency, which makes it basically computationally next to impossible to sample enough independent configurations within the, limitation of time and resources. So this happens in the following two limits, which both results in huge lattice size. One is from the high NG point of view. This happens when you take the UV limit, right? The continuous limit, you sort of remove the UV cutoff by chopping your lattice finer and finer. And in the condensed matter, it's more like when you encounter phase transition and your correlation length sort of blows up. Okay, so that's the disease. So what's the remedy we want to propose? So the basic idea is to use a flow-based approach. So what does it mean? So we have the space of field configurations. So this is a space we integrate over. And then we take another space, an auxiliary space that's called a latent space. So in our in this special case, we will choose the latent space actually to be isomorphic to the configuration space, okay, and to the physical space. And now we will take our flow or our map to be a bijection, okay. So then what do we do? What we want to achieve with such a map, F? Okay, so we will have a distribution on the latent space that's easy, for instance, a Gaussian or a uniform distribution. And then we compute the push forward distribution, this Q of F here. So this is the push forward. I don't know. I changed those slides, but I didn't save it or something. So instead of plus here, it's a multiplication. Sorry about that. Oh, I don't know what happened. Okay, anyways, it's multiplication. It's the original latent space distribution and multiply a factor that's just given by the Jacobian. Okay, it's in principle very simple math. So what do we want to achieve with this? What we want to achieve is that we put all the non-trivial information about the distribution actually into this map. Okay, so just as an illustration, the graph is here. Whew. Okay, the graph is showing. So we start with a simple distribution. Okay, and then in this case, the F is a sequence of discrete maps, such that if you choose your F correctly, then the push forward distribution will be in some complicated shape, but the shape that you want, the physical system dictated. Okay, so that's the idea of flow-based approach. So when can this flow-based approach actually be helpful? I'll say that when the following three conditions are met. So the first is that the row itself is easy to sample. So we can just sample in the latent space, okay, in the end, and then push the sample in the latent space to the configuration space that becomes your sample of physical state, if you want. Okay, and the second is, okay, the same applies, this is a multiplication. Second condition is that this determinant factor should be easily computed or at least approximated. Otherwise, you shouldn't choose a complicated map that's complicated, so complicated such that there's a big error when you compute the push forward distribution, because everything we're talking about here is like improving the accuracy and efficiency of computation. So such considerations are at the heart of what we're doing. And the third is that, okay, we want this push forward distribution to be a very good approximation of the target distribution, which is given by physics. In this case, it will be given by this Boltzmann distribution. Okay, so we want these three things. We want to find F such that these three things are there. So how do we make sure that I'll start with the last step. How do we make sure that the push forward distribution is a good approximation of the target distribution? Well, we do a training. This is where learning happens. So first we choose an ansatz for the flow. And then this ansatz should already be such that we already know that the Jacobian is easily computable or approximated. Okay, so, and then we parameterize the flow with some parameters that are called theta. And then I will show you the explicit form of the ansatz that we use later. But this is the general idea. And then we find the parameters that minimize the so-called reverse KL cost function. So which is the KL divergence between the push forward distribution and the target or the physical distribution. So this is the physical distribution, let me remind you. Okay, so the KL is defined in this way. So you're basically, and this can be evaluated as some, average in, you just draw in the latent space according to your prior distribution row, for instance, of Gaussian. So this should be easy to do, okay? And then after that, you push forward your sample and then compute the push forward distribution, the log of that, and then the action that's also easy to compute. Okay, so this is a computable thing. And one thing to note is that maybe we're all kind of used to the idea that machine learning requires a large number of data in order to train. But this is not the case here. And this is what people call the bootstrap way of training, if you want, because if you could see, it doesn't require any prepared data, right? So this is key, right? If we already have a large sample of the physical configuration from MCMC, then we don't need machine learning to help us sampling, right? So that's the key. And then this is possible because we use the so-called reverse KL instead of the MLE training or the non-reverse usual KL. But so that's key. Okay, so basically you generate your samples according to your proposal, and then you measure the error from your proposal instead of comparing that with a previously prepared set of data. Okay, so to put that in sort of a flow chart, what we do is we draw samples in the latent space according to this easy distribution, the Gaussian in this case, and then we compute the reverse KL loss. That, of course, depends on the map, and hence, moreover, and hence depends on the parameters of the map, the thetas. And then we do gradient descent towards minimizing this KL divergence. Okay, and then we update theta, and then we look at the current value of KL. If it's still too large, then we do it again. Okay, so if there's insufficient accuracy, we keep training. So when the KL is small enough, then we stop the training. Okay, we save the model with given parameters, theta star, and then we build Markov chains using using samples from this saved model. Okay, so here I should also tell you about something about the last step. How do you build Markov chains using these samples? Well, because, okay, so you sample here and that gets pushed forward to samples in the configuration space, the space you are working in. And but the push forward distribution will only approximate, right, the physical distribution. I don't want it to cause errors in the computation of the VEF, okay, of the observable. So what do I do? So instead, I use these only as a proposal sample, and then I put this in the Metropolis Hastings algorithm. So which means that, okay, I accept this sample configuration with a probability that's given by the minimum of 1, or, you know, this is given by the ratio between the physical probability of this sample and the previous sample already in the Markov chain, divided by the ratio, the same ratio, but now evaluated according to the proposal distribution. Okay. So theoretically speaking, this Metropolis Hastings sampling procedure guarantees convergence. So the sample you build from this, no matter what the proposal distribution is, then it asymptotically gives you, you know, good Markov chain, like in accordance with the physical distribution. But in practice, of course, if you use a proposal distribution, not the push forward distribution, that's very far away, then it gets rejected the whole time, and it takes forever to build chain, and it's not usable. So I mean, if you know the acceptance rate of this, if this rate is on the average about more than 60%, then you know it works well. Relatively well in practice. So that's how we sample. Okay, so yeah, so how do you check the quality of the flow? So this acceptance rate will be a key index to see, you know, how good your target, how good your push forward distribution approximates the target distribution. Okay. So now that's the generality. Let's now be a bit more specific. And before that, I'll say what our basic benchmark is. So this idea is not completely new. It actually has been explored since 2019 so actually we started around the same time by a team from MIT, DeepMind, and NYU. So this very nice group of people. So their first paper focused on just 5 to the 4 theory in 2 dimensions. And so let me, since I'll take it as a benchmark, so let me say a bit about their work, their architecture. So they have this set of like discrete flows and a layer. So the idea is that they split the lattice into a bipartition that's given by the checkerboard pattern. And then they update either only the black or the white in each step. And this kind of special sort of, you know, upper triangle form of the matrix guarantees that the Jacobian is easy to compute. So that's a very smart thing about this, the so-called real MVP flow structure. But the downside is that this checkerboard pattern breaks symmetry, the translation symmetry, for instance, right? The translation symmetry is, the unit of translation is no longer given by the lattice spacing, but by the size of the checkerboard. Right, so so we already knew that this idea is very nice, but it scales pretty dismally with the lattice size. So that puts into question like how practical it is to use the flow-based model. So we've been trying all kinds of different flows, and but I mean, two key ideas are the following. So the first is the symmetries. I mean, so in machine learning, I mean, there's often sort of 2 points of view, which each of them probably is right in different moment. One is that you should let the machine try to learn. You should let the machine learn as much as possible itself without giving too much, you know, inductive bias or prior knowledge into the design of the architecture or into the algorithm. And the second is the opposite, sort of you should use sort of domain specific knowledge and what you know about the system as much as possible. So our point of view is that the symmetries is such, the symmetry of the system is such a key, you know, fundamental feature that it should always be baked in instead of being learned in order to have something that's efficient and workable. So in this case, the symmetries are very simple. I mean, the space-time symmetry is just translation and rotation. And then the global symmetry of the system in the 5 to the 4th example would be just a sign flip. It's just a Z2, very easy. So we would like to bake them in from the start. Okay. So the second idea that we want to pursue is that we would like to use continuous flows instead of discrete flows. So that goes on the name of NeuroODE. I think I put the reference somewhere. Yeah, here. I don't know why it disappeared. Okay, so there's a reference later. So this very nice idea is just that instead of learning a map, you learn sort of the gradient. So you learned this vector, okay? So you solve an ODE instead of solving a flow. So it's a continuous time flow if you want, right? And the time will be T, okay? Right, so initial time you start with a latent space at a finite time, which big T that you just stipulate, and that would be your configuration space. So here the unknown, the flow is specified by this vector, and this is what we learn. We want to learn by, you know, imposing a minimization of the KL loss function. Okay, and then you also want the Jacobian to be easily computed. So here the Jacobian, if you want, is or equivalently the log of P is just yeah. It's solved by an accompanying ODE. So this equation just follows from the previous ODE equation, and you can solve them in parallel with like ODE solver. Right, so that's how you just simultaneously compute the push forward probability actually at each time along this flow. By the way, please interrupt me anytime if there are questions, or you can type in the chat, and maybe I won't see it, but I'm sure the moderator, the chair would see it. Okay, so why continuous flow? Well, some advantages include like flexible choices of the vector field, and there are some considerations about memory lost. And what I like about it is the feel of interpretability. Well, this is still, I don't have anything concrete to tell you right now, but this is something I'm thinking about and working on. So basically this, you know, a latent space, it looks like a free theory because, you know, you just have like a Gaussian distribution. On the other side, you want to mimic and this interacting theory, right? Given by interacting Lagrangian. So you might somehow think about it as a RG4 flow of some sort, or actually an inverse of that. And but as I said, that's just words right now.
And then you have 2 minutes.
Yeah. So, yeah, we focus on this two-dimensional phi to the 4 theory, and our choice is actually a very shallow network, just one single layer, but a single layer of continuous flow. And then our ansatz for the flow vector here is given by, well, this thing. So W is some number, and K of A is like just some time shift kernels. So you can turn on and off certain modes when you flow. If you treat this flow as some particle flows, then that means you can exert some force. And then the frequency in the Fourier modes, if you want. Okay, so that's the ansatz. And then the space-time symmetry, well, we want to bake them in. So that implies, right, if you look at this term, because here's x here and here's y, where y denotes different lattice points. So this just denotes sort of, in some sense, the interaction between the two sides. And we want that interaction to only depend on the distance between the 2 points, not the exact location. And we also want to bake in the global symmetry. And here that's easy. That's just given by, the property that sine of minus x is minus sine of x. So that guarantees that if you start with something that's equivariant, that's invariant under Z2, you end up with something that's invariant of Z2 automatically. So symmetry, global symmetry is baked in, and that's not the case in the prior work in our benchmark. So yeah, so here, since I'm out of time, so here's some graphs showing that actually, indeed, sometimes machines never learn the symmetries, in fact, no matter how long you train it. And then this is sort of the key result. So dashed lines are our model, and the solid lines are, the real MVP model, our bench work. I should also say that in their work, they already benchmark against the traditional Monte Carlo. So that's why we don't benchmark against, traditional Monte Carlo. So you could see that the scalability is way better. For instance, the purple line is L equals 32, and let's just look at the acceptance rate, the quantity that we have talked about, and you could see that this is not workable. This is below 5%, while our case is like easily beyond 60% without too much tuning. And we also did some ablation study to show that symmetries really help. And then, well, another lesson is like deeper is not always better. We can ponder about why later, but let me just finish with this last slide. So the future, yeah, there's a lot to do. So on the physics front, of course, our goal is go to QCD. So yeah, so we need to consider fermions, and we will start with considering gauge symmetries. Okay, introducing gauge symmetries. And on the AI front, the complexity and the prior knowledge, the huge amount of prior knowledge we have about these theories actually makes it a very ideal place to test, new methods in sampling. And we also hope to have something to report on interpretability. Okay, so thank you very much for listening.
Okay, thanks, Miranda, for a nice talk. We have 2 questions. Sven?
Hey, yeah, thanks for the very interesting talk. So I have a question on building in symmetries in the neural ODE. So in the sense, okay, you showed the example with the Z2, but you have an idea how to do this when we're thinking about different symmetries like SU3, etc., that become relevant for other examples down the line, how to go about the basis functions for the respective kernel that you
Yeah, so clearly we've been thinking about that, having a QCD in mind. But I mean, are you referring to global symmetry? I mean, or gauge symmetries?
Both in some sense.
Both,
So in a sense, yeah, I mean, there's a story, right, about equivariant nets, but in that sense, like where things are well under control, so to say.
Yeah,
but
yeah.
in the continuous case, I'm not so, yeah.
Yeah, so here the key is the equivariance, at least in the global case, it should be rather straightforward because the equivariance condition is this blue line. So if you identify in some sense the action on the field configuration with the action on tangent space, that's what we always do. That's what we do all the time as physicists, right? So keep that in mind. And then the condition we would like is that this X is you know, some configuration. Okay, not the lattice site. I'm sorry for the, so this is phi if you want, but you want the, if you transform your fields, then the result is the same as transforming sort of the vector. So like here, this in the sine and cosine case, it's clear. So this holds. If this holds for the whole group, then you're okay. You can always build something equivariant. So you just need to find such base function such that this is satisfied in the global case for global symmetries. Yeah, and then for gauge symmetries, it's much trickier. Okay, you can choose to only work with gauge invariant quantities on both sides. For instance, like the Wilson line, you know, like whatever. That's one approach, but there are other approaches like how you flow in the it's also related to the question of how you flow in the curve space, right? In the right, so yeah, so we have like collected many ideas and we're planning to try them out one by one. I mean, right now we just did some little tests on U1. So I think this is in some sense really experimental science, right? So I'll let you know what works and what not, and hopefully in not too long, too distant future. Thank you.
Yeah, thanks.
Okay, we also have a quick question from Fabian and Jim.
Hi, Miranda. Great talk. Quick question. So first of all, I know you know this, but to clarify to anyone in the audience, the basic framework that you're using is building on top of the 2019 work of Shanahan et al. But you're trying to address this scaling problem that is like the central problem in the community. And my question is, you introduced two new things as far as I can tell. One is the continuous ODE approach, the continuous normalizing flows. And then the other is equivariance with respect to global symmetries. They have equivariance with respect to gauge symmetries, but you're also doing equivariance with respect to global symmetries. In terms of scaling up these improved results that you had, do you have a sense of which was the crucial bit, the neural ODE or the equivariance with respect to global symmetries?
Yeah, so the equivariance you could see, like here we slowly we did this ablation study.
Yeah.
So the green line is our model.
Yeah.
And then blue line is that we give up spatial symmetries like rotation.
Yeah.
And the red is we give up Z2 symmetry, global symmetry. And the black is we give up everything. And then you could see that indeed, the more symmetries you have, the better it performs. But now, let's hold the thought, this is L equals 12. And then this ESS, you know, is like above 90% in our model, which can be tuned much better, I should say, because we didn't do a great hyperparameter search because after all, we're not the users. But the black is, you know, also approaching 90. And you can compare this with this graph, right? So in real MVP, so this is, so L equals 12, we compare L equals 12 to L equals 12, okay, goes to over 90. Yeah. And the real MVP, goes like this, right? So at least within the 2 weeks, it's still way below 60. So symmetry is not the real game changer. I mean, it helps quite a lot.
Yeah.
But yeah.
But the improvement here is from the ODE part or from the symmetries? I missed that on this plot.
Right. So here I'm telling you, that's the what I told you. What I tried to say is that our model with all symmetry thrown out still way better than real MVP.
I see, which shows that the continuous ODE approach is actually, the continuous flows is a major improvement. Good.
Well, I would be very careful with such a statement because we tried actually all sorts of continuous flow models.
Yeah.
And some of them is comparable to real MVP. Some of them a bit better, but they are all sort of quite a lot worse than the final version that you're seeing here.
Very good. Thank you. I see Eva has a question, so I'll hold the rest of my questions until the discussion. Thank you. Next talk.
Thanks.
Okay. Eva, quick question.
Yeah, if we have time, I was really intrigued by your comment about RG, and you're trying to go from something to a Gaussian, and you might say, you know, a theory is going to either be IR free or UV free. So if you don't care which direction your flow is, except for very exceptional circumstances, which nonetheless theorists talk a lot about, you know, where it's a fixed point, almost all the time it's actually flowing free in one direction or the other. So that sounded good, but you were cautious about that interpretation. Is that because it's not really a quantum field theory process, or I'm just wondering, could you argue that it is indeed going to go to a Gaussian in one direction or the other?
We're doing one experiment, well, with this team, and it's also relevant, the key theme in my collaboration with another team. So I'll describe maybe both of them, and you will see like what I'm trying to see before I want to say this with a bit more confidence. So where is that slide? No, it's a bit earlier. Yeah, here maybe, do it here. Right, so we want to see this as some free theory, and this clearly approaches our desired theory, interacting theory. And what we want to do is that we can compute this along the flow. Right, so we can compute the distribution here, and we want to match it up with an action. So we're in the process of doing this experiment just to see what the action would look like all along the flow. And if that fits the, this is in some sense nice about it is that you can do experiments before you make claims. So if the flow in the action space does resemble something that we expect from RG, then I'll be happier to. But I mean, it's very, very tempting. I mean, the Polchinski RG equation, I mean, you would think that, I mean, at least theoretically speaking, it should give you something that could work like this. And then, we're also, so in the other, in another collaboration, we're also trying to build indeed just an RG inspired model. And then if that works well as a machine learning model, then again, I'll be happier to feel that there's real content in this kind of interpretation. So in one way, on the one hand, we're just, we have this model that works, and we try to see if in the action space it does look like an RG. And the second way, we try to build in by hand that it has to look like an RG. Then we want to see if it works as an ML model.
Okay, in lieu of time, shall we defer this conversation for the discussion session and proceed to the next speaker?